This week we are going to do the experiment number 7, double pipe heat exchanger. It is also called as pipe-in-pipe heat exchanger. First, objectives. The objectives of the experiments. Number 1, to study counter current and co-current flow for double pipe heat exchanger. Number 2, to find overall heat transfer coefficient for double pipe heat exchanger. Number 3, to study effect of increasing hot water temperature on overall heat transfer coefficient. And if you want number 5, it is little difficult. We can skip for exam, but it is important for the bachelor study to find effectiveness of heat exchanger. This concept is very important, and just I will introduce what is meant by effectiveness of the heat exchanger. So equipment description and specification, we have a heat transfer service unit and we have a tubular heat exchanger.
This week and next week we are going to do the experiment on heat exchanger. Okay, so we have the service unit HT30XC heat exchanger service unit, and we are doing experiment on first week a tubular heat exchanger. Okay, then remove these screws. Okay, and then how to remove the pipe. So this washer we need to push it and we need to pull the pipe. So I will push this washer and I will pull this. So before that you need to close these walls, then also this. Yes, and now this is one cold water is remaining, so I will remove this cold water. Yeah, so this I can remove this and I can put the plate type of heat exchanger, or I can put this tubular. So this week we are going to do this tubular heat exchanger. Okay, so again how to connect it depends on. Now just press it. So red color, take the code, understand the color code, and now this just push it, and then cold water is for blue color and blue color, push it here. Okay, and then put this on the hole and just any two or all, doesn't matter, we can put it to next week. I will explain you the water flow. Okay, so this is a cold water. Cold water is coming from, so we need to make it on. So if you on it, the cold water will flow from here. From here it will come here and it will become here, and this thermocouple will give me the cold water temperature. Okay, the cold water is flowing like this, like this, like this, and it is coming out, and through this point we can drain the cold water. Okay, so this is outlet temperature of cold water, this is inlet temperature of cold water. Okay, now hot water, how it will flow. So this is a tank. In tank the water is heated. This is a temperature sensor. This is for control. If you want heat this water up to 50 degree, so water will be heated up to 50 degree and heater will be switch off automatically. Okay, maximum temperature is 50, 60. So we can set 3 readings, 45, 50, 55. So water will be heated up to that and it will be switch off automatically. Then this hot water is pumped here by using this pump, and it will be flow here. So here this sensor will give you the volume flow rate, F hot. So hot water is flowing here, and this sensor will give you volume flow rate, discharge, liter per minute. Discharge, you study in fluid mechanics, liter per minute. So this water, hot water will come here, and we can measure the temperature of hot water by this thermocouple. So hot water will flow through this inner tube. What is meant by double pipe? There is a big pipe and there is a inside small pipe. Okay, so this big pipe is arsenic or glass, and inner pipe is a steel. Okay, so hot water is flowing through the inner pipe and cold water is over inner pipe in big pipe. Okay, so hot water will flow here like this, and here, and it will go for here, and here we can measure the outlet temperature of hot water, and it will go back to the tank. So here what we need to measure, we need to measure 4 temperature: inlet for cold water, outlet for cold water, inlet of hot water, outlet of hot water. So these 2 thermocouples are not useful. It is a intermediate. Intermediate means this plus this divided by 2 is equal to this average. I need to connect, suppose hot water is flowing through this in direction, I need to make the hot on, okay, on. Now hot water will flow like this, so I need to measure this temperature T1. So this I will connect to T1, okay. So this thermocouple 1 2 3 4 5 6 7. So how to connect that I will show you in the diagram. You can click on start. In program you will find the arm field. These are the different types of heat exchangers. You can choose a tubular heat exchanger, or on the desktop there is a tubular heat exchanger. I make a shortcut. Now here 2 operations are there: counter current and co-current. What is meant by counter current? If water is flowing like this, and if hot water is flowing like this direction, and cold water is like this, then it is opposite direction, then it is called counter current. If both waters are flowing in same direction, it is called co-current or parallel flow.
Yeah.
Parallel flow heat exchanger. Understand? So today first we will select counter and then we will select co-current. So click on counter and load. These are the various windows. Now this is a diagram. This is a graph. I can change the temperature. This is a Excel sheet. I can record the readings. There is a help also, and one presentation is there, PowerPoint presentation. Okay, so I can learn here how to learn this, how to operate this machine. So my important is view diagram. Okay, now see, hot water inlet, hot water outlet, cold water inlet, cold water outlet. Okay, 4 temperatures. It is shown T1, T3. T2 and T5 is not important. I will not connect it. Okay, so T1 and T3, and this is T6 and T4. Now I don't know which is inlet, which is outlet. I don't know here, because if I change the direction, the inlet and outlet will be changed. So how I can change the direction? I can change only for hot water by reversing the pump. I can change the direction of pump by selecting at the beginning counter or co-current. Now this is connected now. Now we'll come back to our experiment. So see this thermocouple 5. So I will find the thermocouple 5. It is a green color. So this is 5. I will choose at 1. The case side should be that side. I will connect it here. So is the 1. This is T1. Okay. Now T3. T3 is outlet. What is the number of this? 3. So I will choose the orange color for 3. I didn't connected this. Okay, 3. Now 4. Inlet. What is the 4?
Inlet,
4 is inlet or outlet, I don't know. So I will choose any one. So this is blue color is inlet.
Because
okay.
We choose counter.
Yes.
We started here then, what?
Yes. Now here we need to important. Now this is a hot water inlet. Okay. For counter, this should not be inlet. This should be inlet.
Yes.
Okay. So what is the number of this? Is T6. So this is number 6. I will connect to blue color 6. Okay, and then this will be 4. Remaining last is 4. 4 number yellow color. I will connect to 4. This is a thermocouple connection. Now this is connected. USB is connected there. Now make a main switch on. Okay, and this start means pull out. This light will be run. Now I need to run from the computer. Now I will click on this power on, and you can see the green light is there. You can see the green light is on. Means the control is here now. If green light is not on, the control is not there. So this is power on. Okay, so once you make the power on, then I will start the heater in the tank. So here heater you make it automatic. So heater will be automatic. So I set here 45 degree. Heat the water up to 45 degree and then switch off the heater, automatic. Understand? And then I will click apply. Okay. Now heater will start heating the water. Okay, then now pump, flow, water flow. Click on flow and then make it manual here. I'm not going to make automatic. And I will increase the pump power up to 35 or 40. 30, 35, and see here flow.
The cold water flow is 2.38 adjusted and it is not working, so it is a direct, so no need to increase this number 4, 5, 6, no need to do that because we don't have controller for cold water flow, so we can adjust it from the inlet water tap, and you can make it partially open or close to adjust this flow rate manually. So this is not working. Now click on the hot water flow. To adjust hot water flow, click on the flow. So this window will be displayed, and here, so we'll use the manual and we'll increase the manual input. So this manual output is a voltage and current, 50% of power, 30% of power. So if you increase the power, the flow rate will be increased, and no need to change anything here because we selected manual and manual output. And you can see now the pump power is 30% input and the flow is showing 0.68 liter per minute. So don't select automatic here, so no need to change anything here. So click on apply and say OK. The flow rate is adjusted to 0.72. Okay. Now click on heater to start the heater. So we can click automatic here, and now heater will start automatically, and manually output here no need. And now set point, I can make it 3 set points: first trial, second trial, and third trial, 45, 50, 55 degrees centigrade. So what is the meaning of? So first reading 45, second reading 50, third reading 55. So when if you write here 45, the heater will be off at 45 degrees centigrade automatically. So heater. And if you make it 50, the water in the tank will be heated up to 50 degrees centigrade and it will stop automatically. Now you can see the water temperature in the tank is start increasing. So here we use a manual, and for heater we use a automatic. That is the difference only. Now this is a 31 degree and 27 degree, 28. So this is inlet temperature of hot water and this is outlet temperature of hot water. And now here we can see that 25.8 is the inlet temperature of cold water and 26.3 is outlet temperature of cold water. So here the hot water inlet and cold water inlet, it shows, but it is a graphical representation because maybe our mistake in thermocouple connection, or no problem, this is not a mistake. So if we change the water flow from here, it will change. So this is a graphical representation. Don't go on this counter or core current. It is showing a counter current. Now click on the Excel sheet, and now you can see the temperature here recorded: T1, T3, inlet or outlet temperature. I need to see the number. And T4 and T6 is a for cold water. T1 and T3 for hot water, and T4 and T6 for cold water. As T2 and T5 thermocouples we didn't connect it. Now click on view diagram and see now 44 temperature is reached to a 55 near about. So we can start. We can click the on 47, so we can start recording the reading. So how to record the reading? So here you can see there is a go The green color go button is there. If you press this, the all reading, all data will be recorded in the Excel sheet. Click on the view table, Excel sheet, and now we can click on go. We can click on go, so data will be recorded here. See now. Yeah. So 54 and 43. So inlet temperature of hot water and outlet temperature of hot water. And here see now T6 25.9 and 28.44. So inlet temperature of cold water is T6 and outlet temperature of cold water is T4. So TCR and TCO, THI and THO. So we need to record from here. So T1 is TH. Select the 5 samples, then we'll click on the stop and we will choose any one reading from that. Click on the view diagram and now click heater and we will do the second reading. So change here the setting. So now we will set this to the 60 degrees centigrade automatic. 60, the water will be heated up to 60 degrees centigrade and heater will be off. Now this temperature will be raised to 60, near about 60. We can click on go. Just to wait for a moment so that we can collect another 5 samples and then click on the stop. Click on view diagram, view table and see the samples are collected or not, and then back click on the. Now click on view diagram, click on heater, and set the here 55 temperature setting, apply OK, and now wait a moment, click on view table and click on go button so that we can record the another set of samples. Once samples are collected, click on stop and then view diagram. So click on view diagram, click on heater and set the another setting as a 60 degrees centigrade. Click apply and OK, and then wait for the some temperature to rise. Now temperature is reached near about 60. Now click on go and click on table and wait for another few samples to record. And when samples reach 15, now this is 9, 10, 11, 12, 13, 14, click on the just wait for 15 and then click on the stop, and now view table. Make the heater off and apply OK. Flow rate is 58. Now we can decrease this flow rate slowly to 0. Flow will off the water flow. So temperature is 62. So let it cool slowly for safety. We need to decrease the water flow rate slowly, otherwise the water remains heated. So we have to wait to drop this temperature. If you increase the mass flow rate of hot water, then temperature will be dropped very fastly. So it doesn't matter, 60 degrees centigrade is not too much temperature, so we can make the flow rate off. Then cold water also we can make it off. So here we are not going to change from here, we are going to change and make the machine power off from here. Yes, and now record the readings from the table. Now we'll save the file and exit the Windows, and from desktop we'll double click on the tubular heat exchanger, click on concurrent operation, select power on, and view diagram, and then we'll adjust the heater voltage, which is control, which is shown at the red inlet and outlet. Click on the control and select the heater voltage to 45 degrees centigrade and adjust the hot water flow rate, and we will repeat the procedure for 3 different heater settings. And at last we will save the Excel file by recording the data for 3 different settings. So click on File, Save As, and save this file as double pipe co-current section and save on the desktop. Okay. So we have these 2 files, and now we can turn off the machine. The heater is off. Now the hot water inlet temperature will start dropping because heater is off. We need to decrease the hot water flow rate slowly and manually close the cold water flow rate from the water tap. And now make the power off. This we are going to close the water manually from the pipeline tap. Now power off. Now open the Excel file from the desktop. Now we will record the readings, and now we have the 13 samples. So from 13 samples we will choose 3 different readings and we will tabulate in the table. So choose any 3 readings for counter current operation. Then double pipe, again we will choose 3 readings for co-current from this Excel file. So how to choose? And now I will highlight this by the color. So we'll choose one more 55 setting or 55, anyone, it is up to you. And then the first 60, 55 and 54. So
This is THI. This is a THO temperature. Now this is TC. This is TCI, and this is TCO.
the 6 readings we need to record in the observation table. Now the last reading I will choose for 50 setting, then 45, 43 I will choose this. Also we have plate type of heat exchanger. Also we have cell and tube heat exchanger. So there are different types of heat exchangers. So plate type we'll study next week. So today we are going to study a tubular heat exchanger. Now about tubular heat exchanger, there is a big pipe. So this pipe is having a inlet and outlet, and there is an outlet here. There is a pipe inside the tube. Now this is a double pipe heat exchanger, or we can say this is a tubular heat exchanger. So red color is a tube inside, and you can see from the side view it is a small circle, and the black color is a big pipe. Now here our main task is to find out what is the diameter of this outside tube, DI and DI and DO, inner diameter and outer diameter. Then we should know for small tube, capital small d and small do. So it is having inner diameter and outer diameter, and this value is given to you 0.006, and inner diameter di is given as 0.0083. So outer diameter, if it is given, it is good. If it is not given, we can find out di plus 2t is equal to, that is 6 into 2 is 12, 12 and 83, 0.0095. So all the dimensions are written. So these dimensions you need to record in observation table. If hot water is flowing through this tube at a rate of MEH, EH for hot, M for mass flow rate. So the hot water mass flow rate is MEH. It is having density rho H, specific heat for hot water H. The hot water is entering through the inner tube at a temperature of TH, T for temperature, H for hot, and I for inlet, THI. It is living with THO. The mass flow rate will not change, density will be changed, specific heat will be changed. That depends on the temperature, because density and specific heat is the function of temperature. Mass flow rate neither be created nor be destroyed. It will not change. The cold water is flowing through this tube at a temperature. Suppose this is an inlet. If this is an inlet, so TCI, temperature of cold water at inlet, and this is TCO, temperature of cold water at out. So cold water will be flow like this direction, and hot water will be flow like this direction. That's why it is called counter. Counter means opposite heat exchanger, double pipe heat exchanger. Okay, so this is the first type we are going to learn, counter current, and there is another type that I will explain you here. I'm not going to change the flow of cold water. Now we'll change the flow of hot water. So cold water flow remains same, and this is a inlet. It is called I. So this is a inlet I. So temperature, cold water is flowing at a temperature of TCI, with the mass flow rate of cold water and specific heat of cold water and density of cold water. So this cold water is flowing through this heat exchanger over the tube and coming out from here at the same rate with a different density, because as temperature is increased here, TCO, outlet temperature of the cold water. We will change the direction of hot water like this. So cold water and hot water is flowing in the same direction. That's why it is called a parallel flow heat exchanger. The inlet temperature of hot water, THI, at a rate of EMH, ρH, CPH. Okay. So this type of heat exchanger is called a parallel flow heat exchanger or co-current double pipe heat exchanger. So today we are going to do the experiment on counter current heat exchanger and co-current heat exchanger by changing the hot water direction. Now this is about the experimental setup, and now all these parameters we need to be measured. So we need to measure the four temperature, TCI, TCO, THI, THO. So THI is generally kept constant, and we are taking three readings for THI, 1, 2, 3, and we'll find all the temperatures keeping mass flow rate constant for cold water and for hot water also. So we are keeping cold water mass flow rate constant and hot water. So for further study or for any project work, you may change the mass flow rate of hot water and find out the overall heat transfer coefficient, or you can change any parameter and compare the heat transfer coefficient, overall heat transfer. So this is about the equipment description. Now we'll start the analysis, how we can find out overall heat transfer coefficient and the effectiveness of the heat exchanger. Now observation, whatever we wrote there, you can write here the observations of the observation. The inner diameter of inner tube, it is called as DI is equal to 0.0083. Thickness of inner tube is T is equal to 0.006 meter. So we can find out outer diameter. And number 3, heat transferring length of the inner tube is given 0.66 meters. So these parameters are very important, and the water property table, it is very important. Now we'll come back to we'll do the experiment and we'll record all the data. So counter flow operation. So particulars, what are this? Symbol VO, I will explain this. And units from the computer machine. So we can take the readings directly from the computer. So we can vary the THI 40, 50, and let us 55 degrees centigrade. Now what is this symbols? I will explain back again here. So MH. So in the machine we have, from equipment we have VH. VH is a hot flow rate in liter per minute, and here we have cold V, volume flow rate, or discharge VC. So we have VC, volume flow rate in liter per minute. So from this, by multiplying densities, so we'll get mass flow rate in kg per second, density is kg per meter cube, specific heat is kilojoules per kg Kelvin, and it's liter. So we need to convert this in meter cube per second, and if you multiply by density, we'll get kilogram per second mass flow rate. So that is mass flow rate mh is equal to density into discharge. In fluid mechanics we study. So kg per meter cube into meter cube per second. So volume flow rate should be in meter cube per second. So meter cube get cancelled. We have kg per second. So this is about the volume flow rate. So from computer we need to get the values from VH and all temperatures, 4 temperatures, and volume flow rate. Then we can do the calculation. Now what is our how we can find out overall heat transfer coefficient? So as hot water flows, it will lose the temperature, and cold water temperature will increase. So heat is lost by the hot water, and that heat is gained by the cold water. So heat lost by hot water is equal to Q. Q is for heat for hot water is equal to mass flow rate, specific heat of hot water, into THI minus THO. Similarly, heat gained by cold water, QC is equal to MC, CPC, TCO minus TCI. So both heats are same. Heat lost by hot water is equal to heat gain by cold water. And from that, can find out heat lost by hot water or heat gain by cold water. So by knowing the temperature, so we can take the average temperature and we can find out the specific heat. We can find out the mass flow rate by knowing the density. If you plot the temperature variation for hot water and cold water, if you consider this as inlet and outlet, number one, suppose this is a counter current and this is co-current. So for counter current first, so hot water. So where is the hot water entering? From this side, hot water is entering, and from this side, cold water is entering. So hot water, it is entering from here. It is the highest temperature, THI. So hot water temperature will be decrease in this direction, and we'll get a THO. The cold water is entering from this TCI, and its temperature is increasing, and here you will get TCO. So this is called a counter current operation. Similarly, for parallel flow, you can see co-current, the inlet is here, so hot water is flowing here and cold water is flowing here. So cold water is flowing here, TCI, and here we'll get TCO. Same THI is the highest temperature and it is coming out as THO. Now hot water will lose the heat, THO, and cold water will gain the heat in this direction. So this is called co-current heat exchanger. Suppose this is a inlet I and this is an outlet O. So here the inlet is I and here outlet is O. Okay. So what is the temperature difference at the inlet? So let it assume delta T I for inlet. So temperature difference at the inlet terminal is THI minus TCO. And here this is a delta T at outlet. So this is terminal outlet. So it is THO minus TCI. So this temperature difference and this temperature difference at inlet and out. Similarly for counter flow current, this is a inlet. So I can write delta TI is equal to THI minus TCI. Similarly at outlet, delta T O is equal to THO minus TCI. Very simple. Okay. So this is the inlet temperature difference and outlet temperature difference. Same for counter flow and co-current flow. Overall heat transfer coefficient, it is denoted by U0 and is given by is Q. Q is equal to heat loss by hot water or heat gain by cold water. It is same, is equal to U overall heat transfer coefficient into area into delta T. Which delta T? There are a lot of T here. So this any one of is not taken. The log mean temperature difference is taken. Log mean temperature difference is called as LMTD. Log mean temperature difference. And this log mean temperature difference is same for parallel flow and counter flow. There is a big derivation how it is same and where LMTD is equal to delta TLM is equal to delta T at inlet minus delta T at outlet divided by Ln natural log delta Ti by delta TO. So the same formula is used for counter current and co-current, but delta Ti is different for counter current, delta Ti, THI minus TCO, and delta TO is this, and for co-current it is different. So this is the change in counter current and co-current. Everything is same, all terminology is same, all formulas are same, only delta Ti and delta TO is different for counter current and co-current. Also, the area A, which area is considered here? It is very important. Now you can see the hot water is flowing from this and the heat is transferring from the inner tube in this direction. So there is a heat transfer. So how many types of heat transfer take place here? Here the heat transfer first is this U consists of conduction and convection. So inner tube and the thickness and outside is a cold water. Outside is a cold water. Okay? And inside is a hot water. So from hot water, the heat is transferred by convection. It is H, and then from inner surface to outer surface through this thickness due to the thermal conductivity of the metal. It is a metal, so it is having thermal conductivity, so heat is transferred from this end to this end by the conduction, and from this surface to the cold water by again convection. That is why it is called overall heat transfer coefficient, and this is given by this. So here we are considering a small thickness and conductivity we are going to neglecting, but it is termed as the overall heat transfer. Now area. So heat is flowing through this inner tube. So the length is given to you, and this is a double thick tube. So it is having di and do. So which diameter is taken? This is a circular. So dm is taken as di plus do by 2. So dm and L is known. We can find out the heat transferring area by dm L. So this area is very important, where dm is a mean diameter of the tube. So we know diameter, we can find out average diameter, and we can find a length is given to you, so you can find out area. So area is known. LMTT is just I calculated here, so area is known. So I can choose any one Q. Q is known from the above formula, so I can find out overall heat transfer coefficient. Okay. The next objective, effectiveness. What is meant by effectiveness? The effectiveness of the heat exchanger. This is a little advanced study, and you will study in BS. So we can skip this also for our sociology, or we can keep it. We will decide this, depends on the theory. So effectiveness of the heat exchanger, if you want phi, it is denoted by psi. It is like efficiency, but efficiency word is not used for heat exchanger. It is not it's a machine which is giving a output. So this heat exchanger is a mediator, translator, or a agent between two things. So how we can say it is efficiency? The heat exchanger don't have efficiency like a agent. So the agent is communicating between two parties, and he is getting his benefit. Like a heat exchanger also communicating between two fluids and transferring the heat. So that's why it is called effectiveness. How he is effective? If he is good effective, then heat will be transferred more. So remember, the efficiency word is not used for the heat exchanger, and it is replaced by efficiency is replaced by the effectiveness, and it is like a efficiency, So effectiveness is defined as the ratio of actual heat transfer QH or QC, anyone, because it is same QH or QC, to the maximum possible heat transfer. What is meant by maximum possible heat transfer? So it is, I will consider QH or QC or QC divided by maximum possible heat transfer. Very important. Qmax. So how I can calculate? Qmax. This is little advanced. So knowing the Qmax is a little difficult. So Q is equal to mCp delta T. Now I have QC and QH. Which is maximum? Both are same. QC and H is same. But there is a particular point where the heat is max. So here THI and TCI is minimum. So here the heat transfer is minimum. Here THI, TCO is maximum. But maybe the difference is same. This difference and this difference same. So I can't say it is a Qmax. But the specific heat increases, the density increases, then temperature difference, if it is constant, then I can say the maximum heat transfer is here. So it is very difficult to find out the maximum heat transfer. Now here I can see THI and THO, the maximum temperature difference. So delta T is maximum, and here it is minimum. Okay. So here the density is very minimum. Here density is very high. Here specific heat is very high, but density is low. So it is very difficult to decide. So this MCP is called a heat capacity, C into delta T, where C is equal to MCP. So I need to calculate CH, and I need to calculate CC, heat capacity of hot water and heat capacity of the cold water. So it is nothing but MHCPH, and this is MCCP. So as temperature increases, decreases, these properties are increasing, decreasing. It is very difficult to find out. So we know these values find out this number, and which is minimum we have to consider. So C minimum is considered maybe CH or CC. If C minimum is there, the temperature difference is very high. So we'll get Q max. So from the C minimum is known, delta T. So delta T is very high. At the entrance only THI, because this is very hot and this is very cold temperature. So here the temperature difference is the maximum. So we can take this as Q max is equal to C minimum into THI minus TCI. Effectiveness of the heat exchanger is equal to, if I consider hot water, MH, CPH, THI minus THO divided by C minimum, THI minus TCI. So here maybe MH, CPH or maybe MC, CPC. So this will get cancelled and here we'll get this. This will get cancelled. If hot water is minimum and this is hot water, it will get cancelled. Or if I consider cold water, MC, CPC, TCO minus TCI, and C minimum, THI minus TCI. Okay, so C minimum may be MH, CPH or MC, CPC. So this will get cancelled, or it is we need to check. So effectiveness of the heat exchanger, and we need to check for the parallel flow and counter flow. So let us do the experiment and take the readings. Now counter current operations. So we'll write the readings, and the first reading is a V hot. So what is this? Volume flow rate of hot water, or it is called discharge. Its unit is liter per minute and its value is 1.95. Then THI, inlet temperature of hot water, THI degree centigrade, and it is 39.9 degrees centigrade. Outlet temperature of hot water is, and it is 36.5 degrees centigrade. V cold, volume flow rate of cold water, and it is 1.916 liter per minute. Then inlet temperature of cold water, 26.1 degrees centigrade, and outlet temperature of cold water, TCO, is degree centigrade and it is 28.7. Similarly, we'll take out for 15 and 55 degrees centigrade. So this, what is this? We need to keep the hot water temperature heater 45, 50 and 55 at setting. So the water inside the tank will be heat up to 45 and the heater will be off automatically. So almost the inlet temperature will reach up to this 39.3, will reach up to 45. Then we need to record all the reading. This temperature will try to reach up to 50 and the heater will be off. So this temperature is not important, it is a setting. And now calculate. And this is a calculation table. So we'll do the calculation and transfer the values here. So this is a flow chart, how I can make the, first I need to find the average temperature, and then from property table I can choose specific heat and density, then I can find mass flow rate, then I can find heat lost by hot water, then I can find LMTD, and then overall. And another objective I can add here is a effectiveness of the heat exchanger, and it is denoted by psi. Okay, so we can add this if it is included in the theory, or if it is not, we can skip. But I will explain here for your further study or this. So I will transfer the co-current operation data also. Same, you can write this as usual. So same, right from the top, same everything, same unit, you can write from the top, and I will give you the readings. So readings from machine is, the volume flow rate is 0.97 for hot water. The temperature is 39.5. I think this setting is 40 degrees centigrade. So this is 36. Outlet temperature of the hot water is 36.7. Then cold water flow rate is 1.19 and inlet temperature is 26.5 and outlet temperature of cold water is 28.7. Now we'll do the sample calculations. So it is very lengthy, but it is having a fixed path and the formulas are very simple. My target is U overall heat transfer. U is equal to UA delta TLF. So I need to collect all the parameters required to find U. So first, the simplest form is the area, and it is common for both heat transferring area, equal to A is equal to pi DML, where dm is equal to di plus do by 2. So di is, so I can find out area is equal to 01845 meters square. So I will find the average temperature of hot water and cold water. So for counter current and co-current, so average temperature of hot water and average temperature of cold water. T average of hot water, TAVG, AVG for average, and TC average, AVG. And for co-current also we can find, and it is almost same. We can find it, check it now. So for counter current, T average is THI plus THO by 2, and here TCI plus TCO by 2. So current THAVC is equal to, and we'll get near about 38 and 27, near about, around, approximately. No need to calculate. There is no change in counter current for average temperature. So we'll choose the properties of water at 38 and 27. Number 2, properties of water at T average is equal to 38.2 degrees centigrade and TC average 27.4 degrees centigrade. The properties for counter and co-current we will use same properties. So it doesn't matter. So which property I need? Specific heat and density of hot water. So specific heat of cold water and density of cold water. So go to the table and find out this. So how to find out this? I will show you the table. The table is given to you. This is specific heat, kilojoules per kg. How to read this temperature? What is temperature now? The temperature is 38.2. So this is 30 and 38. 38 is here. So 30, 30, 31, 32, 33, 34, 35, 36. So this is at 38 we will choose. Okay. And density at 38. So 30, 30, 32, 34, 36, 38, 993. Same for cold. It is a 27. So I can choose 27. Where is 27? This is 20. So for cold water, this is 20. 27 is here. And density is in between these two, 996.4. So we can write these properties in the table, from the table. Properties of water at the average from table. So specific heat of hot water is 4.1781 kilojoules per kilogram Kelvin or degree centigrade, and density is 993 kilogram per meter cube. At 27, 4.1786. See, higher temperature, lower specific heat, and lower temperature, higher specific heat, and density is more, 996. Cold water is heavy and hot water is light. So once we know the properties, we can find out the mass flow rate. Number 3, mass flow rate of hot water and cold water, that is mH and m. So mH is equal to rho h into vh, volume flow rate, discharge. So rho h is 993 into vh is 1.95. See, can I do the multiplication? No, control Z. Density is in kilogram per meter cube and volume flow rate is 1.95 liter per minute. Okay, so I need to change the unit here. It should be a SI unit. So 993 kilogram per meter cube into 1.95 into 10 to the power minus 3 meter cube. 1 liter is equal to 10 to the power minus 3 meter cube. And minute is nothing but 60 seconds. So this meter cube and this meter cube get cancelled, and your answer is kilogram per second, 0.03223 mH. Similarly, I can calculate the cold water flow rate. MC is equal to rho C into VC, volume flow rate, 0.01976 kilogram per second. So number 5, temperature drop in hot water is equal to delta T H is equal to THI minus THO. So THI is 0.4 degrees centigrade. Similarly, temperature gain in cold water. Cold water is equal to delta Tc is equal to Tco minus Tci. 0.6 degrees. 6. Heat lost by hot water. This is my objective. So what is the heat gain by cold water? I will not consider because my attention is focused on hot water only, not on cold water, because it is MHCpH delta TH. So QH is equal to kilogram per second, kilojoules per kilogram Kelvin or degree centigrade, and this is degree centigrade or Kelvin. So this get cancelled, kilogram get cancelled, kilojoules per second is nothing but kilowatt. 0.45784 is equal to 457.84 watt. Now my aim is 7 log mean temperature difference. Log mean temperature difference, it is called LMTD. It is denoted by delta TLM or theta m. In some of the book it is used theta m and theta I, theta O. So we'll use delta TM. So log mean temperature difference is given by is equal to delta TI minus delta TO divided by ln delta TI over delta T. So here the counter flow and co-current flow is, the formula is same, but the answer will be different. How? Now for counter current, hot water, cold water, TCI, TCO, this is THI, and this is THO. So this is inlet, and this is outlet. So what is delta TI? Delta TI, THI minus THO. So delta THI minus THO, suppose this is 39.9 and THO is 28.7 and delta THO is 36.5 and this is 26.1. Delta TO, this is for outlet, 36.5 minus 26. THO minus TCI. Don't memorize formula. This formula will change for counter co-current parallel flow. So just remember this diagram and write from here this minus this and this minus this. 10.4. If you memorize, then you will confuse in counter and co-current. So just draw the diagram and assign any inlet and outlet. This is inlet, and this is outlet, and then find out difference. Then I can find out delta TM, delta higher divided by lower, higher minus lower. If you have lower, then it will be a minus, and there is no ln for minus. So your answer will be 10.795 degrees. This is log mean temperature difference. Q is equal to UA delta TLM. So I know this, QOH number 8. Overall heat transfer coefficient is given by U0. Q is equal to QH is equal to U0 area delta TLM. U0 is equal to QH over area delta TLM. So I know everything. I will put the values. So U is equal to area is 0.01845 meter square. Delta TLM is 10.795 degrees centigrade. Q is 457.84 watt. The answer is 2298.766 watt per meter square degree centigrade. This is overall heat transfer coefficient. My objective is finished. Last objective is optional, and just I will explain in very short, and that is N9. Effectiveness of heat exchanger is given by psi is equal to, so I have QH, so Q max I don't know, so QH and Q max is C minimum into THI minus THO. So I will simplify this. What is C minimum? Where C minimum is from TH is equal to MHCpH 0.1347 kilowatt per degree centigrade or Kelvin, and Cc is MCCpC. Your Answer is 0.08258 kilowatt per Kelvin or degree Celsius. So this is a minimum. So here C minimum is E is equal to CC is equal to 0.08258. So this is effectiveness is equal to QH is, this is watt, 0.4578, and CC minimum is 0.08258 into THI minus TCI, 39.9 minus 26.1, and you will get effectiveness is 0.4017, is nothing but 40.17%. Similarly for co-current. So this is a lengthy report, just I am telling you because we need to do the double calculations, but almost the calculations are same. So similarly, number one, the area is same. Now area is not going to change. So number two, I will find the average temperature of hot water, hot and cold water. So T average, TH average is equal to THI plus THO divided by 2 is equal to 39.5 plus 36.7 divided by 2 is equal to 38.1. As I told you before, it is same. And TC average is equal to TCI plus TCO divided by 2 is equal to, as I told you, the properties of the fluid 38 and 27. So we'll take number 3, properties of water at TH average. So at TH average is 38 degrees centigrade and TC average is equal to 27 degrees centigrade around. We'll take it same. CPH is 4.1781 kilojoules per kilogram Kelvin and density is 993 kilogram per meter cube, and here CPC is 4.1786 kilojoules per kilogram Kelvin and rho C is 996.4 kilogram per meter. Number 4, mass flow rate of water. mH is equal to rho H VH, mc is equal to rho C VC is equal to rho H 993 into VH for counter current 0.97 into 10 to the power minus 3 meter cube and divided by 60 seconds. We will get this as 0.01605 kilogram per second. Temperature drop in hot water. At cold water, no need. Delta TH is equal to THI minus THO. THI is 39.5 minus 36.7, 2.8 degrees centigrade. And temperature drop in cold water, delta TC is equal to TCO minus TCI is equal to, anyone we can choose. Number 6, heat loss by hot water or heat gain by cold water. We can calculate QH and QC, anyone, MH, pH, delta TH, MH. 2 is equal to 0.14756 kilowatt and 147.56 watt. But this is in kilo. So QC no need. Even this no need. Now next 7, LMTD, log mean temperature difference. LMTD is equal to delta T LM is equal to delta Ti minus delta To divided by Ln delta Ti divided by delta To. So how to get delta Ti, and this is important for us. So everything is same. Now here it is a difference. For co-current, draw the diagram, a very important diagram. Draw the diagram. So this is THI, this is THO, this is TCI, and this is TCO. So write the values here. This is 36.7, this is 28.7, and this is 39.5, and this is 26.5. So what is the difference here and what is the difference here? So delta Ti. So this is the inlet. So here it is a inlet and here it is a outlet. So delta Ti, Thi minus Tci, Thi minus Tci. Don't memorize this formula. Just remember here. 10 degrees, so maximum temperature difference. And delta TO 36.7, 28.7 is equal to 8 degrees centigrade. So LMTD, delta TLM is equal to 13 minus 8 divided by ln 13 by 8 is equal to 10.2984. So this is for co-current, and counter current it was 10.79. So this counter current is more powerful and this is less effective, not powerful, effective. So counter current is more effective than co-current. This is one of the objective, one of the conclusion. So LMTD is degree centigrade 10. So I can write the conclusion as counter current is more effective than co-current. Now LMTD is known. Now I can find out overall heat transfer coefficient. Overall heat transfer coefficient is equal to U is equal to U naught is equal to QH or QC. QH divided by area into delta TLM. QH is 147.56 divided by area is same 0.01845 into 10.2984. So here you will get 776.61 watt per meter square degree centigrade or Kelvin. So this is for co-current, and counter current 1100 something, and for co-current 776. So counter current heat exchanger is more effective than co-current heat exchanger. So 9 effectiveness of heat exchanger sigma is equal to QH divided by Qmax. So where Qmax is equal to C minimum into Thi minus Tci. This is always maximum temperature difference. So I need to find C minimum. So CH, heat capacity of hot water, MH, CPH, CC, MC, CPC. So put that value, MH is 0.01605 into 4.1781 is equal to 0.06706 kilowatt per Kelvin. Or degree centigrade, and this is 0.01976 into 4.1786 is equal to 0.0826 kilowatt per Kelvin. So C minimum is equal to CH is equal to C minimum is equal to CH 0.0670 kilowatt per Kelvin. Now I can find effectiveness. Qmax is, because it is kilowatt, so I will take this kilowatt. 0.14756 divided by 0.06706 into THI. THI is 39.5 minus 26.5 is equal to 0.169%. I can write in conclusion, effectiveness of counter current is greater than effectiveness of co-current, so more effective than. So counter current is more effective than co-current. Now conclusion number 1, overall heat transfer coefficient for double pipe heat exchanger, for counter current arrangement, and for co-current arrangement. So U0 is equal to, for counter current it is 2298.76 watt per meter square degree centigrade, and for co-current it is 776.61 watt per meter square degree centigrade. LMTD you can write delta TLM for counter current is more than co-current. Number 3, counter current arrangement, counter current flow is more effective, effective than co-current. This is more important conclusion, and now we'll stop here.